Hello everyone, my name is Philippe Habib and today I'm going to give you a small overview about the Graphics Processing Unit or the GPU as part of Dr. Ali Shahab's EEC 321 course. The GPU is also known as a graphics card or plainly a video card. First of all, I'm going to start by telling you what is a GPU or a graphical processing unit. In short, it's a dedicated processor efficient at manipulating and displaying computer graphics. Like the CPU, it's a single-chip processor that could be present on a video card or embedded on the motherboard of your computer. In some cases, it could even be directly embedded in the CPU die. GPUs are essential in modern computing systems because they enable a representation of a three-dimensional world as realistically as possible. So these GPUs are designed to provide additional computational power that is customized specifically to perform these three-dimensional tasks. In this slide, I'm going to tell you what's the purpose of adding a GPU to your computing systems. In general, graphics workload is extremely parallel, which means that a lot of operations have to be executed at the same time to generate the frames that are displayed on your screen. Such operations often saturate your central resources, such as the CPU, the main memory, and the system bus. What the GPU does is provide a separate, dedicated graphics management to relieve that burden off of your main resources. You could expect the GPU to be highly parallel and highly multi-threaded, to be able to carry that workload and to compute a lot of operations at the same time, which optimizes visual computing. What's also great about the GPU is that it works at the same time as the CPU. Here we are going to compare the GPU to the CPU. The GPU has a substantially higher computing density than the CPU, which means that the GPU executes a lot more operations per unit time than the CPU. Because as we may know, the CPU has a complex control logic which has to fetch, decode, and execute operations while dealing with hazards and pipeline stalls, whereas the GPU has high computation per memory access, which means that the ratio of arithmetic operations to memory operations is very high, which makes it perfect to deal with parallel operations such as visual computing. From a hardware point of view, the GPU has a lot more cores and consequently a lot more ALUs than the CPU, even though those cores can be weaker than those on the CPU. This is one of the main aspects that allow the GPU to be faster and to compute a lot more operations per unit time than the CPU. As for memory, the CPU requires a large memory, but with a slower cache obviously, whereas the GPU has a smaller but faster cache. As for pipelines, the CPU has shallow pipelines with less than 30 stages, while the GPU has deep pipelines going to hundreds of stages. And the CPU has low latency tolerance, while the GPU has high latency tolerance, which all allow it to be a lot faster than the CPU. Looking at the overall architecture of a CPU and a GPU, we can see a lot of similarities between the two. Both use the memory constructs of cache layers, memory controller, and global memory. A high-level overview of a modern CPU architectures indicate it is all about low-latency memory access by using significant cache memory layers, which we saw in the previous slide. Whereas for the GPU, it looks like the nature of a GPU is all about putting available cores to work, and it's less focused on low-latency cache memory access. Notice how the CPU has a large control unit and large cache, whereas those two units are a lot smaller and divided in the GPU, and how the CPU has fewer ALUs than the GPU. In fact, this is because the GPU focuses on executing arithmetic operations, which are done by the ALUs. Now let us focus more on the GPU architecture. A single GPU device consists of multiple processor clusters, seen here in the dotted blue areas. Now each cluster contains multiple streaming multiprocessors, seen here in the dotted violet areas. For each streaming multiprocessor, we have a layer 1 instruction cache layer with its associated cores, and the cores contain the ALUs that execute the arithmetic operations. Typically, one streaming multiprocessor uses a dedicated layer 1 cache and a shared layer 2 cache as seen here. And that before it has to pull data from the global DDR5 memory. The general architecture of a GPU is very tolerant of memory latency, or memory access delay. Compared to a CPU, a GPU works with fewer and smaller memory cache because the GPU has more transistors dedicated to computation, because it has a lot more ALUs and a lot more cores, and it cares less how long it takes to access the memory. In fact, this memory access delay or memory access latency is masked or overshadowed as long as the GPU has enough computations to keep it busy. Now, if you take a quick look at the number of cores in the GPU, you can quickly understand why it's designed to operate parallel instructions or operations. In this slide, we're going to discuss the GPU pipeline, or the steps taken to transform a 3D object in the graphics application into a 2D image on the screen. First, data is fed into the bus interface, where commands are processed. We start with the vertex processing. It converts each vertex into a 2D screen position. Then clipping removes the parts of the image that are not visible in the 2D screen, such as the backside of an object. We then go to triangle setup. Vertices are collected and converted into triangles. And rasterization is the process of filling those triangles with pixels known as fragments. Afterwards, the pixel shader adds texture and final colors to the fragments and gives the pixels their final attributes. And finally, the pixel engines mathematically combine the final fragment's color, its coverage, and degree of transparency with the existing data stored at the associated 2D location, to finally display your 2D image on your screen. In this final slide, we're going to discuss the GPU applications. The first main application is in gaming and video editing, because both of those tasks require a huge amount of computational power, and what the GPU does is take that load off the CPU and frees up memory to increase performance from one side and to provide smoother and more realistic graphics. Another application is in artificial intelligence acceleration, since neural networks in AI require a lot of computational power that are quite similar to those in image manipulation, because they're very parallel tasks. A lot of tasks have to be done at the same time. GPUs are great to do that. And finally, GPUs are commonly used in cryptocurrency mining, since to mine cryptocurrency, you need to solve a lot of computational problems to add to the blockchain. And to do that, you need huge amounts of computational power, which are provided by GPUs.